Hello, this is Nitin Dahak with the Times. I'm talking now to William Ruby, who's responsible for power efficiency at Synopsys. William, hello.
Yes, hi Nitin. Thank
How-
you for the opportunity.
How are you?
Very good. Yourself?
Good.
Yeah.
Tell me what power efficiency is a big
Yes.
thing right now. So tell me what your role entails.
Yeah. So I'm responsible for the product management aspect of the Synopsys, what I call dedicated power analysis solutions, and then the spectrum of power analysis. We'll talk more about this. Is covering really the entire space from architectural design to the hardware design, also known as RTL design in the vernacular, and implementation sign-off. So my responsibility is the power analysis backbone of the entire Synopsys flow. And the product management aspect is essentially working with our customers to define the roadmap, the capabilities that we need to develop in these products going forward, work with our engineering team to define these capabilities in more detail, really, look at the release schedule when a different capability is coming out, keeping our customers informed, working with our field applications engineering team to have them understand what the new products or new features are all about, how they can be used by our customers better.
Well, I mean, it sounds like you're horizontal across everything at Synopsys because power is so important right now for power consumption.
Right. So yeah, because it's really, again, I kind of look at this as the analogy that I always use is, designing a chip is kind of like building a house, right? You're building a house and you start out with an idea, a concept, and then you say, okay, well, now I need to draw up some architectural plans, right? So you do the design of the architecture of the house. But then if you have a contractor coming in and, let's say a carpenter, he says, well, I can't really work with the architectural designs. It doesn't have enough details, so you need to do blueprints, right? Yeah. And then these blueprints become the guide for the construction, and the parallel to the chip world is implementation.
Right.
And then the final inspection that needs to be done for the house is equivalent to what we call sign-off analysis.
Sign-off,
right?
okay.
So really, it's that whole spectrum.
And then you've got the verification.
Yes, that's right.
Now, let's talk about some of the industry trends. I think for several years now, I've been hearing keynotes at conferences like DAC, where we get data suggesting the power demand of the electronics in this world is going to exceed the supply. Right. Is that real? And sort of what are the things we're doing about it?
Yeah, so I see the same trends, and I firmly believe that trend is very, very real and at the same time very disturbing, right? Because we fundamentally see that the energy consumption is going up to the point where in a few years it may exceed the energy production. And then we're going to be limited by the amount of energy that we can produce. And there are a lot of different factors that are contributing. So I'm talking about the overall energy supply and energy demand. We'll talk a little bit more about AI applications. I know you talked about with the Stelios about the use of AI technology within the Synopsys products, but we have customers who are designing chips and systems for AI applications. We have electric cars that all need to be charged, and everybody's on their mobile phones. Of course, those need to be charged up as well.
Yeah.
So there is that really, really growing trend, disturbing trend, as I said. And one data point that I wanted to add, I just read something very interesting in the report. It said that a ChatGPT request compared to a traditional, let's say, Google search takes up an order of magnitude more energy to complete.
I've heard that in the last few months as well.
Yeah.
So it is something that we need to be looking at in
That's
terms
right.
of, I mean, what are the things that you think both Synopsys is doing as well as industry to optimize that or make it more efficient?
Sure. So that's a really good question, and I also wanted to take a kind of like a step back. I've been involved with this in low power or energy efficiency for a long time.
Yes.
And what happened in the past is that even in the early days, designers needed to sort of analyze power consumption, and what they did is they worked at a very, very low level of abstraction because that's where the accuracy was. So they trusted those early, the estimates in those days were based on, transistor level, spice level type analysis, maybe moving up to gate level, because that's what they trusted. But if you look at the potential of improving energy efficiency, it really is driven by architectural decisions. It is really driven by even software, hardware, partitioning, and so on. So I think that a lot of people now are recognizing that, but the interesting thing is that the design technology, the tools that we use, evolved in the opposite way.
Really?
They evolved bottom up. We started at a very low level of abstraction because that's where we can get accuracy. But now we're moving.
You need to go top down now.
Exactly,
Yeah,
exactly.
I mean,
So
sorry. Go on.
so that's the whole notion of maybe a little bit of an overused term called shift left, right? So the shift left.
Okay, yes, I hear that a lot, and sometimes I wonder whether it's some new kind of way of describing things. But I guess it's just moving everything from one place where you've been doing things to somewhere where it's earlier on or higher up.
Yes, exactly. That's what that is. Yeah.
So yeah, I mean that's going back. But then, so what are the things that you're seeing?
So what are the things that we're seeing, right? So if you want to look at energy efficiency, for example, energy power analysis, anything to do with power consumption, requires basically a view of what is the activity in the system. What is the design actually doing? What application is it running? And ultimately, what is the workload that design is actually seeing as it's operating? And again, the traditional way of analyzing something like that was to create some simulation test benches and run a simulation and then do some power analysis based on that. But those simulations, also we call them synthetic vectors, may not represent the real use case.
Oh, yeah.
So the trend here is to really use the application workloads to do this early power analysis, right?
It's almost like the digital twin of that.
Exactly right. So because you want to make it something that's real, a real workload. And but the issue that comes in there is that a real workload or an application is huge in terms of, if you look at things like the data set, huge in terms of, let's say, how many clock cycles does it take? And like Carl Sagan used to say, billions and billions, right? Billions and billions of clock cycles. So how do you handle something like that, right? So we have ways to handle it. And the way that we handle it is that we have our hardware-based verification platform, the emulation capability. So instead of a simulator, you would work with an emulator. So you have an actual software application running, producing activity that the emulator can then process, and then create what we call an activity database. It's a compact representation of that, billions and billions of clock cycles of data. And that representation can then be analyzed by our technology to create a power profile. So the user can actually see, not just looking at the number by itself may not tell you much, but looking at the profile of power consumption as the application is running.
And those power profiles will be different for different applications, whether it's the mobile and low power, or consumer, or data centers, or automotive.
Exactly.
So you're looking at all of those, are you?
Right. So we're working with customers who are designing edge AI applications. We're working with customers who are designing mobile SoCs. We're working with customers who are designing high-performance computing chips.
The biggest impact, I guess, is at the data center level. So that's where you can make a lot more efficiency. Is that right?
So in the data, so here's an interesting thing about the
Yeah.
data center. So if you look at the power consumption of these data center chips, they're like in hundreds of watts. In some cases, they're getting up to a kilowatt.
We've seen the presentations from NVIDIA.
Yeah. So and then that's what the liquid cooling comes in to cool these things. But here's an interesting. So from the data center side, here's one thing that the customer told me that said, okay, we have a certain power limit. Let's say, let's call it, a kilowatt, let's say.
Yeah.
We have a certain power limit, but what we want is we want performance. And what we want, and the reason why we want to improve energy efficiency is not to ultimately get lower power. We can still be at that 1,000 watt limit, but within that limit, we want to go as fast as possible.
Yeah, I think everybody would want to do that.
Right. Okay. So that's.
It's just like when you're driving a car, you want within your budget to do as good a performance car as possible.
Exactly. Now, on the mobile side, one of the ways that our customers get design wins is they say, we have lower power. We have a lower power spec. The functionality may be similar, but our power consumption is better. So they get a design win. So it's a competitiveness for.
Right.
And then there's another aspect of this, which is the edge AI type applications, right? Which is now if you look at the application space there, it's pretty broad, and that also needs energy efficient designs. So I have a data point here for you. This is one of our customers. They published this in the user group at Synopsys, and so it's a public domain information. It's a startup called Sima.ai, S-I-M-A.ai. So what they did is that they used this emulation power analysis technology that we have. By the way, it's called ZeBu Empower. You may be familiar with ZeBu as our hardware platform. ZeBu Empower is the power analysis companion.
We saw it at one of the keynotes from you at Snowco. I mean, Sassine or Art.
Right.
I think,
But what SEMA has done is that they said, look, holistically, they started looking at their architecture. They started looking even at their software. They have a compiler that they use. And over the course of several months, working with this technology, analyzing profiles, optimizing the architecture, controlling memory accesses, they were able to get, from the starting point, a 2.5 times improvement in energy efficiency, or they call it performance per watt.
Okay.
Not 25%, not 2.5%, but 2.5 times.
That's a significant difference.
Yeah.
Just something you said earlier, and I just wanted to make sure you clarify the distinction between simulation and emulation, and what's the impact of what's the distinction and also impact of those.
Right. So the distinction is that the emulation represents a real world use case.
Okay.
Okay. Whereas simulation is something that the engineer tries to do to maybe try to mimic that work. So, engineers are only human. Yeah. We all can make mistakes. And in fact, a lot of times what we see is that the simulation-based approach does not really cover the real world use case. Okay. So what are the things that can happen? They can underestimate power consumption, which is obviously pretty important. But the other thing is that if they are looking at a particular segment of that profile and say, okay, we want to optimize for this part of the work, of the simulation workload, it may be the wrong interval. It may be the wrong area to really focus your optimization efforts. Sure. Where the real workload will show you what exactly it is, right? So the productivity, ultimately the results can suffer.
So William, what are the sort of key things you want our audience to sort of know on the power efficiency side right now?
So on the power efficiency side, I would say a couple of things. Start thinking from the start. Very importantly, make power or energy efficiency one of the primary criteria when you are looking at the architecture of the design, when you're looking at IP selection for the design, even the technology selection. So start considering power early on, as early as possible, to make intelligent decisions.
Is that easier said than done?
In some sense, yes, but my favorite, one of my favorite sayings is it's not black magic, it's just good old-fashioned engineering, right?
Yeah, we were hearing that a lot about security
Yeah.
over the years, but I think now people are getting it. So
Yeah. So fundamentally, whether you start using spreadsheets, early analysis tools, looking at the power and energy efficiency from the get-go is really, really important.
Okay.
The other part of it is to recognize that the design process has multiple stages in it. You have architectural design, you have the hardware RTL design, implementation, and sign-off. So energy efficiency, in my mind, is sort of like an equal opportunity challenge. Even though the opportunities sort of diminish to reduce power as you go forward, but if I can get 10 or 15% through my implementation flow in terms of power optimization, yes, I'll take that.
Yeah.
So every stage can contribute to power efficiency.
Yeah.
And in some cases, what we see, for example, is that despite the best efforts in architecture, in the hardware design stage, the RTL design stage, you can still introduce what we call power consumption bugs.
Okay. Yes.
Basically wasted power conditions.
Okay.
So you have to be careful about that.
Okay.
Okay? And then in the physical implementation flow, longer routes, over-designed clock trees, all of that can lead to wasted power consumption as well.
Well, it sounds like some good tips there
Yeah.
for some of our audience. So, William, thank you very much.
Thank you. Thank you.